Okay, the first thing that we'll do is get familiar with Visual Studio 2013 and the directory structure for our software. If you extract the bonus files that you find on the associated website, you'll see something that looks like this. So we've got a build directory. You won't have the content in the included and lib directories quite yet. You will the first time you build the projects, but those will be built on the fly. So you'll have build and external and source. The build directory contains the OpenGL.sln solution. So that's the solution that is going to contain all of the Visual Studio projects that we have for all of the lessons. And the external directory has a series of external third-party libraries. And we'll see these here in just a few minutes when we get inside of Visual Studio. But to mention what these are, GL3W is a OpenGL loading library. OpenGL is a cross-platform API, and we needed a loading library from OpenGL in order to load the proper functions for the given platform. So we're using a loading library called GL3W. The next is GLFW. That's the next we'll encounter. GLFW is a framework that makes a few things easier to start up with OpenGL. GLM is the GL math library. OpenGL itself does not include a math library by default. We rely on third-party libraries for OpenGL, and GLM is one that I really enjoy. It's developed in order to mimic what you'll see as we start writing shaders using the GLSL language. So GLM mimics that. Soil, which is the simple open image library, is used for importing PNG files or JPEGs or textures. And the Open Asset Import Library, which is ASIMP up here, is for loading 3D models. So we'll see those here in just a few more minutes as we open up our Visual Studio project. And then lastly is the source directory. If you open the source directory, you'll see a library directory that contains common code that we'll be using for all of our projects. It's populated with quite a few files right now. And then individual projects for each of the lessons. Now these lessons all have files that are specific to that lesson. So for example, lesson 1.1, lesson 1.2, and so forth. You'll notice that there are no directories for lesson 2. Lesson 2 is all about 3D mathematics, so there aren't any demonstration applications that go along with lesson 2. Let's dive right in. Open up the build directory, and we're going to open that up in Visual Studio. And of course, go ahead and build the application. Make sure that you have the latest OpenGL 4.4 drivers for your video card. That's something to note. And notice that in this solution structure, we've got our library project and the series of lessons that you just saw in the directory structure. The library project creates a static library, where each of the lesson projects creates an exe. So the library project is linked. It is a dependency for each of the executables. Let's spend a little bit of time kind of getting used to what's in the library projects and in each of the lesson files. You'll see there are a few Visual Studio 2013 filters for header files and source files. So there are sub-filters for cameras and lights and various header and CPP files. The content directory is specifically for models and effects. You'll be hearing a lot more about vertex and fragment shaders here, but the library project then contains all of the content that is for all of the individual lesson projects. So the lesson project, it has just the individual CPP files and header files for a given project. And we're going to start off very, very simply with lesson 1.1 with just a single file, program.cpp. I want to look at just a few things, and that is include in library directories. For lesson 1.1, in order for us to link to the third-party libraries that I just alluded to and to the library project that's in our Visual Studio solution, we have to set up a few things in our project. So lesson 1.1, open up the project properties and go to the C++ configuration properties section. Under this section, under General, you'll see an additional include directories section. If you can expand that and go to Edit, you'll see a series of macros. These are Visual Studio macros, if you're unfamiliar with them, that basically say, where am I going to find header files that I don't have local to the lesson 1.1 project or to whichever project we're referring to? And the answer is, for the library project, I want to, from the solution directory, go up one directory, and then down into the source directory and into the library directory in order to access header files. Now what that would look like from a folder perspective is I'm in the build directory. That's my solution dir. That's this macro here marked solution dir. I go up one directory, and then down one directory into source, and down another directory into library. Now, all of the header files that are here, that's what is going to be available by specifying this directory as an additional include directory. Similarly, all of the external folders, so GL3W, GLFW, GLM, the Open Asset Import Library, and Soil, they all have individual directories for including header files. So if you look at the external folder, in the GL3W folder, for example, it has an include directory, which has subdirectories for header files. Likewise, if we look at GLFW, it has an include directory called GLFW, and it has a series of header files. This is true for all of these that you see here. Now, you'll see this same directory structure mimicked for all of the lesson projects. Along with the header files, of course, that's just for compilation, but for linking, we need to have access to the library files that are associated with those third-party libraries in with our own library project. The general folder here marks an additional libraries directory section, and if we edit that, we can see a series of directories for finding static link libraries. Now, these could be dynamic. In fact, the Open Asset Import Library is a DLL. But the way that DLLs work, of course, in C++ is we need to have a type library, a linked library to link against that has stub implementations that would then be actually filled at runtime by the DLL. So let's look at solutiondir.lib, and that's back in our directory structure here. Go to build again. We go up one directory, and now you can see there's a lib directory. You'll see this lib directory appear once you build any of the applications. The lib directory then contains output from the library project. The library.lib file and the library.pdb file. The PDB is the program database that contains debug information for debugging our library project. And that's what we get access to when we reference the solutiondir.lib directory. Similarly, the external GLFW lib x86 folder contains the, hop over to that, external GLFW lib x86 contains the GLFW lib files. The GLFW3.lib and GLFW3D.lib, I'm just going to call this out and state that this is a common convention to have the letter D at the end of the file name for debug versions of the library. That allows us to put the library in the same directory for both the debug and the release builds. So we just put a D at the end of it, and we know that that means the debug library, and that's the one that we'll explicitly link to for the debug build of this project. This is true for all of the third-party libraries. So the Open Asset Import Library, the Simple Open Image Library, all of them follow a similar directory structure. Okay. So now let's take a look at the actual program.cpp and our very first OpenGL project. Now, I want to preface this that this will not actually write any fragment shaders or vertex shaders. That's going to come in the very next lesson. But right now, we're going to render a window to the screen and get our first taste of OpenGL. So open up the program.cpp file. The program.cpp file, the first thing that you see there is a #include for comma.h. And this comma.h file actually comes from the library project. So if you open the comma.h file, you'll see a series of header files that are included that we're going to include for pretty much all of these applications. And note that we're including windows.h for all of the Windows API, the exception library we're going to do exception handling and throwing and catching exceptions, and the asserting and the STL strings and vectors and maps, etc. If the preprocessor symbol OpenGL is defined, then all of the OpenGL headers will be included as well. So there's a few things that we need from OpenGL itself. So this is from the GL3W library, so gl/gl3w.h, from the GLFW library, and from the GL math library. So you'll see there's a series of header files that are there. So program.cpp relies on this header file, as will all of the program.cpps, and almost all of our code will rely on this comma.h. If you're unfamiliar with Windows programming, then note the winMain function. This winMain function is akin to the C standard main function. Of course, that's the entry point for all of our C or C++ applications. Well, for Windows applications, this is the same idea, but it's winMain instead of simply main. And instead of a series of just 2 arguments, now we have 4 arguments. The H instance here, that defines the instance of the application that's running. Previous instance actually is no longer used. It will always be null. Command line options, and how to show the window with show command options. But let's take a look at what this application is actually doing now. The first thing to note is that we're going to be creating a vec4 variable called cornflower blue from the GLM namespace. If you're unfamiliar with namespaces, That : scope resolution operator notes that the vec4 data type comes from GLM namespace. And a vec4 is simply a series of 4 floating point values. We're going to use these 4 floating point values to define the color cornflower blue, which we'll clear our screen with. The next line is if not glfw init. glfw init is one of the first calls we have to make since we're using the glfw framework. Now we're going to augment the glfw framework with our own rendering engine, our own rendering framework, but we're going to use the glfw to bootstrap our efforts. And the first call to glfw has to be glfw init, and if it fails, then we're going to exit out of the WinMain application with a -1. The next command is to declare a glfw window pointer and create it with a glfw create window command, and in this case, creating an 800 by 600 window with the title OpenGL Essentials. And if that succeeds, all is well. We'll go on to glfw make context current, which passes in the newly created window. OpenGL has contexts. In fact, we need to have an OpenGL context for any interactions that we do with OpenGL. And glfw make current context is what provides us that OpenGL context. Think of the OpenGL context as our communication path between the application and the API. gl3w init is the next call, and gl3w recall is the loading library. If we hop into gl3w init here real quick, we'll notice that the load procs function, let's look at that, that's what is actually doing this pointer fix-up for Windows-specific functions to OpenGL counterparts. So we're actually going to always use the OpenGL syntax, in this example, GL call face. That's one of many OpenGL functions. Note that all of the OpenGL functions start with the lowercase letters GL. And these are simply loading all of those functions for the particular driver that we have for the platform that we're running on. So gl3w init is necessary in order to set up OpenGL on our Windows platform. And then we call gl viewport to define where we're going to render to the window that we just created. We can actually create a sub viewport. We don't have to render to the entire window if you don't like. But the gl viewport command lets us define a subsection of that. We're going to use it in the same dimensions. So 800 by 600 will be the very same dimensions for gl viewport as the glfw create window call. The next call is an infinite loop here that says while glfw window should close, while it's not closing the window. And when is it going to get the command glfw when should close? Well, that's going to happen when you click the X button, the close button in the upper right-hand corner of your Windows. So if that's not the case, then this loop will continue to run, and this is what would be called as the game loop or the run loop. So if you've ever heard of the term game loop, this is what they're referring to. The first thing that we'll do inside of the game loop is clear the color buffer. Now, the term frame buffer, we'll get into this a little bit more when we talk about the OpenGL pipeline, but there are various outputs that we can write to. But the first output, the one that we're going to concentrate on here, is the color buffer. The color buffer in the example that we're using here, this 800 by 600 display, we're going to have 800 by 600 fragments or 800 by 600 pixels that we're writing to the color buffer. And what we're doing here by specifying GL clear buffer is giving them a static color of cornflower blue. So we're writing every one of those pixels to the cornflower blue color. Now, again, I mentioned that GL commands all begin with the GL lowercase letters. They also end with this strange looking syntax perhaps. The F stands for floating point. So GL clear buffer means that the input that's coming, one of the arguments is going to be floating point, and that's the case here for this vector. And then V means vector. The word vector here, don't be confused with the mathematical term vector. Vector here just means an array of floating point values. So the syntax that you see here, the address of cornflower blue sub-0, that just gives us an array, a pointer to the first of these 4 floating point values. And we're going to take those 4 floating point values and use them for every single color in the color buffer. To note, the color buffer, we mentioned that its dimensions are 800 by 600, but its color depth by default is 32 bits per pixel. So there's 4 bytes for each of the pixels in that color buffer. If you notice, there are 4 floating point values in this vec4. So it's 4 floating point values that we're going to store inside of each pixel of the color buffer. The next command is glfw swap buffers. And your rendering that actually happens, most of your rendering will happen between a clear buffer call and the glfw swap buffers call. Swap buffers indicates that we're using a multi-buffering rendering system. And what that means is, in this example, it's actually using double buffering. In double buffering, there are 2 color buffers actually. One's called the front buffer and one's called the back buffer. we are rendering to the back buffer while the monitor is displaying the front buffer. So the idea there is that we can eliminate tearing or reduce tearing by not allowing the monitor to display data from two different images simultaneously. So the swap buffers command won't happen until all of the rendering, which again is going to happen in between these statements, which could be lots of rendering, right? It might take several milliseconds to render all of your data. And then we'll call glf swap buffers to say we're done with the back buffer. You can now present it to the front buffer. To note, this is often timed, the swapping is often timed with something that's called the vertical refresh rate of your monitor. The vertical refresh rate, or VSync, vertical synchronization, VSync, is something that we'll do, again, in order to eliminate tearing. We want to render the back buffer to the screen while that vertical sync, and I'm drawing a diagonal line here with a mouse pointer to denote what's actually happening there. The monitor is rendering every one of your pixels line by line, and when it gets to the lower right-hand corner, it comes back to the upper left-hand corner and draws again. Well, during that process, in old cathode ray tube monitors, it was an electron beam, right? And during that time of that electron beam coming back to the top of the upper left-hand corner, and now, of course, it's just how long does it take for me to begin energizing the upper left-hand corner again. The refresh rate is how many times that happens per second, and then in between every one of those refreshes, that time can be synchronized with the glfw swap buffers call. To do that, it's the glfw swap interval command. Finally, we're going to call glfw pull events, and this allows the glfw framework to process any mouse or keyboard events that have happened. Very, very important, because if we didn't call glfw pull events, it would never register the window command for glfw window should close once you hit the close button on the window. So that loop would last forever. We need to call glfw pull events frequently. This is typically done once for every pass through the run loop. Finally, when we do exit out of our window and the window is about to close, we can call the glfw destroy window and glfw terminate commands just to clean up our application. So let's see how this behaves when we run it. So let's run the application. And we have a window that's cornflower blue, and it has the title OpenGL Essentials. And that's it. I know that's a little anticlimactic for our first application, but we're going to get much more sophisticated with this very, very quickly. In the very next lesson, we're going to add vertex and fragment shaders, and we're going to rewrite this a bit to be more extensible. So this is the base code that is necessary to create any OpenGL application using the glfw framework, and it's what is going to act as our background to all of this. But we're going to make this a bit more extensible.